Welcome to the deep dive. Today, we're opening up a research paper that, well, it didn't just nudge things forward, it really fundamentally changed how we build models for handling sequences. Text, language translation, maybe even paving the way for audio and video down the line.
Absolutely. We're talking about Attention is All You Need, came out in 2017 from researchers at Google, Vaswani, and others. If you're working with LLMs or any modern sequence stuff today, this paper is like ground zero.
Right. And our mission today is to really get into it. What was this new architecture they proposed, the transformer? And that title, that claim, attention is all you need. Why so bold? How could just one mechanism replace what came before?
Well, to really get that, you kind of have to picture the scene just before 2017. For sequence tasks, especially translation, the dominant models were recurrent neural nets, LSTMs, GRUs, that sort of thing. You also saw some convolutional approaches. And yeah, attention mechanisms were being used, but usually layered on top of these RNNs. They weren't, the main engine.
Okay, so let's paint that picture. What was the big headache with those recurrent models? Why were they hitting limits?
The main thing was they were inherently sequential. And RNN processes input one step, one token at a time. It keeps this hidden state trying to summarize everything it's seen up to that point.
Right.
But that step-by-step process makes training slow. You basically have to wait for the previous step to finish before you can compute the next one. It's fundamentally hard to parallelize across the sequence length.
Okay, so slow training, because you can't process the whole sentence at once easily. And what about understanding relationships across the sentence?
That was the other big challenge. Because information had to pass sequentially through that hidden state, connections between words far apart in the sentence could get, washed out.
The signal degrades.
Exactly. The path length for information was long, proportional to the distance. So capturing those long-range dependencies, really tricky. Attention on top helped. Sure, it gave shortcuts, but the underlying RNN was still the bottleneck.
And then this paper comes along and just says, let's just ditch the recurrence and the convolutions too while we're at it.
Precisely. That was the radical step. The transformer architecture threw out recurrence and sequence-based convolutions entirely. It's built purely on attention mechanisms and relatively simple feed-forward networks.
So attention is the core. Let's unpack that. What is this attention mechanism actually doing according to the paper?
Okay, so the paper describes it abstractly as mapping a query and a set of key value pairs to an output. Think of it like this. The query is kind of like your current focus, what's relevant to me right now.
Okay.
The keys act like labels for different pieces of information, the values. The attention mechanism calculates how well each key matches your query. It computes a compatibility score.
Right.
Then it uses those scores as weights. It takes a weighted sum of all the values, where values with keys that match the query, that'll get higher weights.
Yeah.
So the output is essentially an aggregation of the most relevant information for that query.
Ah, okay. So it's like searching through a database where the keys tell you what's in the values, and the query pulls out the most relevant stuff and blends it together.
That's a really good way to put it, yeah. And the specific type they use is called scale dot product attention. It's very efficient. You calculate the similarity between the query and keys using a dot product.
Got it.
Then comes the scaled part. They divide those scores by the square root of the dimension of the keys. This is a neat trick, actually. It helps prevent the dot products from getting too large, which can cause problems with training, especially with the softmax function later.
Softmax?
Yeah, after scaling, they apply a softmax function to the scores. This turns them into probabilities, basically weights that all add up to 1.
Okay.
And finally, you multiply those weights by the corresponding value vectors and sum everything up. That's your attention output.
Okay, so that's one attention calculation. But the paper talks a lot about multi-head attention. What's the idea there? Why multiple heads?
All right, this is crucial. Instead of just doing that scaled dot product attention once, multi-head attention runs several attention calculations in parallel. Before doing the attention, it first projects the queries, keys, and values into different, usually smaller dimensional spaces. It uses different learned linear projections for each head. So each head gets a slightly different view of the Q, K, and V.
So each head is doing its own scaled dot product attention calculation.
Exactly, in parallel. So you get multiple output vectors, one from each head.
And then what happens to those multiple outputs?
They just get concatenated together and then pass through one final linear projection to get back to the model's expected dimension.
Mm.
The big advantage here is that it lets the model jointly attend to information from different perspectives, different representation subspaces at the same time.
Ah, so one head might focus on, say, syntactic relationships, while another looks at semantic similarity, maybe?
Kind of, yeah. Or attending to different parts of the sequence simultaneously. A single attention mechanism might average things out too much. Multiple heads give it more flexibility to capture different kinds of relationships. The base model in the paper used 8 heads.
Interesting. Okay, so multi-head attention is the core building block. Now, how does it fit into the overall model? They use that standard encoder-decoder structure, right?
That's right. Pretty standard setup for translation. The encoder reads the input sentence, creates a representation, and the decoder uses that representation to generate the output sentence word by word.
Okay, let's start with the encoder. What's inside?
The encoder is basically a stack of identical layers. In the paper, they use 6 layers for the base model. Each layer has 2 main parts, 2 sublayers.
Okay.
The first sublayer is a multi-head self-attention mechanism. The self part is key here. It means the queries, keys, and values all come from the output of the previous encoder layer.
So the input sequence is attending to itself.
Exactly. Each word or token can look at and weigh the importance of all the other words in that same input sequence. It's learning relationships within the input.
Okay, that makes sense. What's the second sublayer?
The second one is a straightforward, position-wise feed-forward network. It's just 2 linear transformations with a ReLU activation in between. It's applied independently to each position, but the network weights are the same across positions within that layer.
And I remember seeing residual connections and layer normalization in the diagrams.
Yep, standard practice by then really helps with training deep networks. They wrap a residual connection around each of the 2 sublayers, followed by layer normalization. It helps the gradients flow and stabilizes the activations. The output dimension of each sublayer, and thus the layer itself, is kept consistent D-model, which was 512 in the base paper.
Got it. So stack 6 of those layers, and that's the encoder. It processes the input, lets all the words relate to each other via self-attention, processes them individually with feed-forward networks, and outputs a rich representation. What about the decoder? Similar structure.
Similar, but with a twist, because it needs to generate the output sequence 1 token at a time. It's also a stack of 6 identical layers in the base model, but each layer has 3 sublayers.
3. Okay, what are they?
First is a multi-head self-attention mechanism, just like the encoder. But crucially, it's masked.
Masked. What does that mean?
It means that when the decoder is calculating self-attention for a particular output word it's generating, it's only allowed to attend to words that came before it in the output sequence, plus itself. You can't peek ahead at words it hasn't generated yet.
Ah, that makes sense. It has to be causal, autoregressive for generation.
Precisely. The masking enforces that. So that's the first sublayer. Masked self-attention on the decoder's own output so far.
Okay, what's the second sublayer?
The second sublayer is where the decoder talks to the encoder. It's another multi-head attention mechanism, but not self-attention. Here, the queries come from the output of the previous decoder layer, the masked self-attention output. But the keys and values come from the final output of the entire encoder stack.
Uh-huh. So this is how the decoder looks back at the original input sentence to decide what to generate next.
Exactly. This encoder-decoder attention lets every position in the decoder attend over all positions in the input sequence. This is where the context from the input really informs the output generation.
Okay. Masked self-attention, then encoder-decoder attention. What's the third sublayer?
Same as the encoder. A position-wise feed-forward network, again applied independently to each position. And just like the encoder, each of these 3 sublayers in the decoder has residual connections and layer normalization around it.
Right. So the decoder uses masked self-attention to look at what it's already said, encoder-decoder attention to look at the input, and a feed-forward network for more processing.
You got it.
But wait, if we've thrown out recurrence and convolutions, how does the model know the order of the words? Isn't the cat sat on the mat different from the mat sat on the cat? How does position information get in?
Excellent question. That's a critical piece. Without recurrence or local convolutions, the raw self-attention mechanism is permutation invariant. It would treat the sentence the same regardless of word order.
Not good for language.
Definitely not. So they needed to inject information about the position of each token. They do this using positional encodings.
Okay, what are those?
They're vectors, the same dimension as the embeddings, D model. They contain information about the position. These positional encoding vectors are simply added to the input embeddings at the bottom of the encoder and decoder stacks.
Added directly to the word embeddings.
Yep. So the input to the first layer isn't just the word meaning, but the word meaning combined with its position signal.
And how are these positional vectors calculated?
The paper proposed using sine and cosine functions of different frequencies. For each position in each dimension of the encoding vector, there's a value calculated based on these waves. The idea, the hypothesis, was that using these periodic functions would make it easy for the model to learn relative positions, because the relationship between the encodings of position pos and pos plus k could potentially be represented by a linear transformation.
Interesting. Did they try other ways?
They did mention in the paper that they also experimented with learned positional embeddings, just learning a unique vector for each position during training, and found it worked almost identically. But the sine-cosine version has that nice property of potentially generalizing to sequence lengths not seen during training.
Okay, so we have the multi-head attention blocks, the encoder-decoder structure, the feed-forward bits, and positional encodings to handle word order. Now we get to the big claim. Attention is all you need. Why was this setup so much better? What were the key advantages over RNNs and CNNs?
This is really where the genius of the architecture shines. It comes down to tackling those core RNN problems head-on: parallelization and long-range dependencies.
Let's hit parallelization first. How does self-attention help?
Well, think about an RNN layer. To compute the state for word 5, you need the state from word 4, which needs word 3, and so on. It's inherently sequential, ON sequential operations, where N is the sequence length.
Right.
In a self-attention layer, the calculation for each word's output depends on all other words. But those calculations can all happen at the same time. There's no sequential dependency across the words within the layer calculation itself. The number of sequential operations is constant, O1, with respect to sequence length. You can basically blast the whole sequence through the layer in parallel.
Wow, okay. ON, sequential steps down to O1. That's a massive difference for training speed, especially on parallel hardware like GPUs.
Huge. Is a fundamental enabler for training much larger models much faster.
Okay, speed boost from parallelization. What about the other big RNN problem, long-range dependencies? Self-attention nails this too. Remember how in an RNN, the path length for information between word 1 and word N is proportional to N?
Yeah, the signal has to travel all the way through.
In self-attention, any word can directly attend to any other word in the sequence, no matter how far apart they are. The calculation for word 1 can directly incorporate information from word N and vice versa within a single attention step. The maximum path length between any two positions in the sequence is constant, O1.
Direct connections, basically. No need to pass messages sequentially.
Exactly. This makes it vastly easier for the model to learn relationships between distant elements in the input or output.
So faster training via parallelism and better learning of long-distance relationships via direct attention paths. What about the actual amount of computation per layer? Is attention more expensive?
That's a good point. The complexity of a self-attention layer is roughly ON to D, where N is sequence length and D is the representation dimension. That N-squared term looks scary.
Yeah, quadratic in sequence length sounds bad. It can be, for very long sequences. But the paper points out that for the kinds of sequence lengths common in machine translation at the time, often using subword units, keeping N relatively modest, and when N is smaller than D, which it often was, self-attention could actually be faster per layer than recurrent layers with their OND2 complexity. And it was competitive with, or faster than, some contemporary convolutional approaches too.
Okay, so computationally, it wasn't necessarily more expensive and maybe even cheaper in relevant scenarios.
Right. And they also mentioned a potential side benefit: interpretability.
Ah, yeah, you mentioned that. The idea that you could look at the attention weights.
Exactly. Because the model explicitly calculates these weights, showing how much each word attends to others. You can visualize them. Sometimes these attention patterns seem to reflect syntactic or semantic relationships, giving you a little window into what the model might be thinking. Although interpretability in deep learning is always a bit tricky.
Sure, but potentially more insightful than a complex recurrent state. Okay, this all sounds fantastic on paper. The real test is performance, right? How did it actually do?
And this is where it really sealed the deal. They tested it on major machine translation tasks, WMT 2014, English to German and English to French, standard benchmarks.
And the results were?
State-of-the-art, by a good margin. On English to German, their big transformer model hit a BLEU score of 28.4. That wasn't just better than previous single models, it beat the best published ensembles combinations of multiple models.
Wow. Beat the ensembles. That's impressive. What about English to French?
Even better, relatively. The big model got 41.0 BLEU, which was a new state-of-the-art for single models at the time.
Okay, top scores. But you emphasized the efficiency angle earlier. Did it deliver on that promise too? Was it actually faster or cheaper to train to get these results?
Yes, and this was arguably just as important as the raw scores. They achieved these state-of-the-art results using significantly less training time and compute.
How much less?
Like orders of magnitude less in terms of training days on GPUs compared to previous state-of-the-art RNN-based systems. For instance, that big English to French model hit 41.0 BLEU training for just 3.5 days on 8 P100 GPUs. The paper noted this was a fraction of the training cost of prior top models. Even their smaller base model outperformed all previous models and ensembles and trained much, much faster.
Better scores and drastically cheaper and faster to train.
Okay, I see why this paper caused such a stir.
Yeah, it was the combination. It wasn't just an incremental improvement. It showed a fundamentally different, more efficient, and more powerful way to build sequence models by going all in on attention. It basically rendered the complex recurrent architectures obsolete for many state-of-the-art tasks almost overnight.
So wrapping this up, what's the big takeaway for listeners? Why does this 2017 paper still matter so much? Well, the takeaway is that this architecture, the transformer, built purely on attention, solved key problems with older models.
Yeah.
Its parallelizability unlocked the ability to train much larger models on much more data, much faster.
Wow.
And its ability to handle long-range dependencies meant those larger models could actually learn more complex patterns in the data.
It basically provided the architectural foundation for the massive language models and other sequence models we see today.
Exactly. It was the blueprint. It made the current era of large-scale AI in language and increasingly other domains computationally feasible.
A true paradigm shift.
Definitely. And thinking about where they pointed next, the authors concluded the paper by saying they were excited to apply these attention-based models beyond text. They mentioned images, audio, video, and also exploring ways to make the generation process less sequential, perhaps using attention more cleverly there too. So, a final thought to leave you with maybe. If this architecture is so good at efficiently relating any piece of information to any other piece within potentially vast sequences, what new kinds of understanding or generation become possible when we point this powerful attention lens at data far more complex than just sentences? What happens when attention is all you need for, say, understanding a whole movie or composing